The last section on the other disciplines FE is thermodynamics and heat transfer. So you will have 9 to 14 questions on this. It will feel like a lot. From what I've heard from people, there is kind of a lot. So this will focus more on thermo and a little bit on heat transfer. So laws of thermodynamics, equilibrium properties, and processes. So like all kinds of different engine cycles and PV diagrams, you'll need to know that. Heat transfer, like conduction, convection, and radiation. Properties in phase diagrams. Psychrometrics, so that's like the wet bulb and dry bulb stuff, and combustion. So all of this is things that you will read from charts and tables, but you have to be able to understand the charts and tables. So let's take a look at the handbook section. So there are 2 sections in the handbook for this. There's a thermo section and a heat transfer section. We'll start here with the thermo. This is a big section, 30 pages. But you don't have to know quite all of it, but they could ask you almost anything. So state functions here, this is basically just defining what all the different symbols are and their units. So some of them are pretty standard. So, you know, pressure, temperature, volume. Specific always means that it is the value divided by the mass. So you can have a specific volume, you can have a specific internal energy, enthalpy, entropy. So all of this stuff, when you're looking up in a table, it will give you the specific value. So then if you want to find the absolute value, you have to multiply by the mass. Now, something like pressure and temperature is not related to mass at all. So in that case, there is no specific version of that. It is just absolute. The 2 different specific heat capacities are CP and CV. So CP will be constant pressure and CV will be constant volume. So if it's a liquid, you can pretty much assume that is going to be a constant volume situation, but with a gas, it could be constant pressure or constant volume. You really need to know in the problem. Also for a liquid, these 2 will probably, CP and CV will be pretty similar. So this section has, towards the end of it, there will be steam tables. So if you have saturated water and superheated water, there will also be some refrigerant diagrams. So properties for 2-phase systems. So this basically shows the amount of gas per amount of liquid, and that's called the quality, denoted by the variable x. It's basically just a fraction of gas over the total mass of what's going on. So if x equals 1, then that would be all gas. If x equals 0, that would be all liquid. PVT, so ideal gas law. There will be a lot of stuff on here. So know the P1V1 over T1 equals P2V2 over T2. That's, I think, Charles's law. And then the general ideal gas law, PV equals MRT. And where R is the universal gas constant. So this is affected by the units. So make sure whatever the units are in your problem that are given is you use the appropriate R value. Now for an ideal gas, CP minus CV equals R. So remember that's for a gas, because for a liquid, these 2 things are pretty similar. All right, so constant entropy, we will have a K factor instead of just being able to use the P1V1 over T1, or PV over T was a constant. For a constant entropy process, you have to find the K, and K is the ratio of CP to CV. A lot of times it would be given in the problem. I think normally for air, K equals 1.4, but don't quote me on that. You will probably want to look at it in a table. So let's see, partial volume. So that is essentially just the part of the volume as a part of the whole, how much is related to the mass. So how much of that gas is in there, and that is the partial pressure of that gas relative to the total pressure. And same thing for volume. You know, the gas will take up a certain amount of space proportional to its mass. If there are other gases in there, there will be proportional to their mass, and so on. Now for real gas, we have PV equals ZRT, where Z is the compressibility factor, and this V here is specific volume, so that is capital V divided by M. So the volume of something divided by the mass, so it's basically the inverse of the density. Okay, first law of thermodynamics. So this is about conservation of energy in a thermodynamic system. The heat is the energy due to temperature difference, and the work is it's positive if it's work done by the system on something else. So like if it's being productive for your life, maybe it is turning a wheel or some kind of moving a load or something like that, that's positive work. If the work is done on the system, like air is compressed, that would be negative work. Now, for a closed thermodynamic system, that means that no mass crosses the system boundary. So a thermodynamic system is closed if everything happens in the same container. It is open if there can be gas that, or mass, any kind of mass that is leaving the system. So an example is a internal combustion engine, like something that's in a gas car or a diesel truck. That is an open system because fuel is being burned up and leaving through the exhaust port. So that is an open system. But a chemical reaction that is taking place inside of a closed container, that is a closed system. Okay. Steady flow system is a system does not change state with time. So this is true for turbines, pumps, compressors, throttling valves, nozzles, and heat exchangers. So if something comes in as a liquid, it leaves as a liquid. If something comes in as a gas, it leaves as a gas. So note that the evaporator is not shown on here because evaporator would take a liquid and turn it into a gas. But the rest of these is assuming that you are working with only gas or only liquid. Okay, isentropic efficiency. So turbines, pumps, and compressors are often considered adiabatic, so this means no heat transfer. So velocity terms are usually ignored because the velocity change is usually negligible compared to the amount of work that is done. So we just focus on the enthalpy change of the system there. A basic cycle, the efficiency of the cycle is the work done divided by the heat that is put into it. So it is also related to the change in heat or change in temperature over the heat that was pumped in. So the Carnot cycle is the most efficient cycle. So you can do it all just based on temperature because that's like as close to ideal as you can get, but you do want to do it in absolute temperature, so like Kelvin or Rankine and not Celsius. Now, other cycles, the Carnot cycle, the Otto cycle, and the Rankine cycle can all be done on PV diagrams or TS diagrams where S is entropy. So psychrometrics are like the sort of water vapor, dew point temperature, dry bulb, wet bulb stuff. What I have heard from students who took it is that they were not expecting this stuff to be on there, but it definitely was. So you'll want to study this section and make sure that you understand about humidity and dew point temperature and wet bulb temperature and all that kind of like weather related stuff. So the second law of thermodynamics is about change in entropy of something, and pretty much entropy is always increasing. It is never decreasing. So maybe it's zero change, but it's definitely never decreasing. And here we have a TS diagram. So this is showing from state 1 at 1 temperature, and state 2, you have a higher temperature and you have more entropy, and this whole area is the heat change. So now combustion processes, this is another thing to know about. Basically, for a combustion reaction, you always have a hydrocarbon plus oxygen makes carbon dioxide and water. That's what makes something a combustion reaction. So if you know what kind of hydrocarbon you're burning, like this one is methane, but it doesn't necessarily have to be methane. This is just an example. You would just balance that reaction, and then you would be able to find what those stoichiometric coefficients are. Okay, most of that stuff here is not important. Okay, chemical reaction equilibria, this one is important. So you will need to know the limiting reactant. This is what would be used up first in a reaction. So it's going to be on the left side because it's a reactant. So which one gets used up first? It'll be one or it'll be the other. Sometimes you have multiple reactants, but that's the one that will make your reaction stop when it runs out. And then the yield is how many moles of the product that you actually got from it if the limiting reactant got used up. So it's the ideal situation. Chemical reaction equilibrium, this is easier to calculate with the formula in the chemistry section. And now we have the tables. So this is a steam table. So saturated water, basically you'll go down this left column. So the temperature in degrees Celsius is on the left, and the saturated pressure is here in the second column. So you would find your appropriate temperature, and then you would be able to find the specific volume, specific internal energy. So specific volume is lowercase v. The internal energy is the lowercase u. The enthalpy is lowercase h, and the entropy is the lowercase s. And this is all per unit mass. So it doesn't depend on how much mass that you have. So then if you find your temperature and say your temperature is in between two of these, like maybe you have an 18 degrees instead of 20 and 15, you can just linearly interpolate between those two. But you do want to know if it's a liquid you're looking at or if it's a vapor, because the vapor will obviously take up way more space than the liquid will. And some of these other properties will also be different. So this is kilopascals and then gets to megapascals once you get to 100 degrees Celsius. So you can use this table for steam or saturated water. Now for superheated water, so this is going to be extra hot, then we have a temperature column on the left, and then we have a whole different group for different pressures. So depending on what pressure that you're at, that will be, there's a minimum temperature for steam to exist at that pressure, because like sometimes, if your pressure is too low, then it won't possibly be steam, it'll just be water. So this is a minimum temperature to actually have that pressure and have steam. So anyway, you'd find your pressure, and then you would go to get your specific volume, your specific internal energy, specific enthalpy, or specific entropy, whatever the question is asking for. Now, this is an HS, or enthalpy and entropy diagram for steam. So here, I'm going to make this a little bit smaller so that we can see the whole chart at once. So what this chart is showing is for lines of constant temperature, which are these lines that go across over here. So the ones that sort of start low down here, go up, and then curve. Those are constant temperature lines. And then we have the constant pressure lines here, which are the diagonal. And then we have the enthalpy on the vertical axis and the entropy on the horizontal axis. So basically, if you're given the entropy or the enthalpy, then whatever pressure you need, you can find the other one. So these lines are for constant moisture. So if you have a 5%, so the saturation line here is between the liquid and the gas. So down here, you would have something that is like really low enthalpy and really low entropy, and the percent of moisture increasing down here. And then at this point, there is 0 moisture, and then above that, you have gas. So all this is gas. All these are like 5%, 10%, 15%, so on, liquid. So then the next table, so this is a pressure and enthalpy diagram for a refrigerant. So different refrigerants will have different diagrams, but they'll all look really similar. So this has a ton of confusing lines on it, but what we want to look here is first we'll look at the axes. So we have pressure on the vertical axis. So in bar or English units on the right, megapascals or metric units on the left. And the enthalpy here, this is specific enthalpy, so kilojoules per kilogram on here. And so all of these different lines, we can see, so the temperature lines here, there are some vertical temperature lines on this part, so -60 up to 40. of these vertical lines. And then we have some more temperature we have on horizontal lines. So on this curve, we go from 90 degrees down to 0 degrees down to negatives, these horizontal lines. Now, the lines here, this big thick black line is the saturated liquid line, and then this one on the other side is the saturated vapor. So the saturated liquid, something is all liquid, saturated vapor, something is all vapor, and so the lines that run sort of parallel to it that all come together at this top point, this is the quality line. So if you know the quality, then you can go up to figure out whatever temperature you would have or pressure. You can kind of figure out all of those things using this particular chart. And then over here, we have different volumes, and this is, again, specific volume and not absolute volume. So the vertical lines here are temperature. The dashed lines here are volume. And then the angled lines, these slanted lines here are entropy. And all of this is the specific version, so this is the mass-independent version. So this is a different type of refrigerant, sort of the exact same thing. We have this saturated liquid, we have the saturated vapor, and we have the changing quality in the middle, increasing pressure on the y-axis, and then increasing enthalpy from left to right on the horizontal axis. We have density is these dashed lines, density in pounds per foot cubed. So all of this, or most of this, is in English units. And then we have temperature in Fahrenheit that's on these vertical lines here with the sort of dashed dot thing. There are some tables where you can also look up properties. And then here we have yet another refrigerant. This will be the exact same way. So if the problem asks you something for a specific refrigerant, just make sure that you figure out the graph, make sure you're using the correct graph. So this is 410A, but there are different ones, and you would just Control F to find which one you need. Tables for that. Now this is thermal and physical property tables. So here for gases, we have separate CP and CV. So make sure you know if you're doing constant pressure or constant volume, and then you can find the appropriate CP or CV to use with whatever gas you're using. And here is steam at the bottom, and here is air at the top. So those will be the most common ones. And this is the K value, that K that I was talking about for if you have the ratios of pressure or temperature or volume and something's to the K or the 1 minus K or some power like that, here's where you will get the K. All right, liquids and solids. Okay, so for liquids, you use CP, constant pressure, because CP and CV are so close, and then solids similarly to that. So you can look it up for the common things here. Air is a gas, so we don't see air in this table because air is not ever going to be a liquid. So this crazy graph is a compressibility chart. So this shows the compressibility factor, which is the PV over RT. So which we've heard the formula PV equals MRT. This is not equal to M because it's using specific volume instead of absolute volume. So it gets a compressibility factor, which is Z. And this was it was in a formula towards the beginning of this section, but you can also find it here on this chart on the y-axis. If you know what temperature then you're at, and you can if you know your pressure, and then you go up to your temperature, then you can find your compressibility factor for different specific volumes. So pressure on the x-axis, these sort of like curved lines are the temperatures, and then the lines that are dashed that sort of go from bottom left to top right, that is specific volume. And this TR is the reduced temperature, so it shows us over here that is actual temperature divided by the critical temperature. Common thermodynamic cycles. You definitely will have to refer to this one. So we have the Carnot cycle here. We have an Otto cycle. We have a Rankine cycle and a refrigeration cycle. So if a problem asks you about one of those cycles, go ahead and draw your diagram first, and then you kind of identify what these specific points 1, 2, 3, 4 are on the diagram. For air refrigeration cycle, so here we have a heat exchanger that takes the heat out, and we have a turbine that actually does the work. We have the air-conditioned space, so like the actual inside of your refrigerator, that would be sucking in the heat from the air, and then we have a compressor that compresses all that air and sends it to the heat exchanger. So this is the physical diagram of the setup, and this is the temperature and entropy diagram where you have heat coming in from the food or whatever it is that you put into your fridge, and the heat going out through a heat pump or heat exchanger. Now here's another psychrometric chart. So don't let this overwhelm you with all of these different lines here. This one's in metric, and so the bottom axis here, we have enthalpy. So this is specific enthalpy. And then that is all these sort of slanted lines that go from top left to bottom right, specific enthalpy. Now these curved lines here are relative humidity. So this is from 10% humidity all the way up to 90% humidity. Those are those curved lines. The enthalpy you can see on here. And then let's see, yeah, and then it comes out here. So this is actually sort of the x-axis and the y-axis all has specific enthalpy, and it comes from this slanted line. And then the wet bulb temperature is what's going on some of these other lines. So the wet bulb temperature lines and the enthalpy lines actually look really close, so try not to get those mixed up. So this is basically contrasting the enthalpy with the relative humidity, and you would have to find your specific point on here. So this is the same thing. This is at sea level. Let's see, what was the other one? The other one was also at sea level. Okay, so what is this looking at? ASHRAE psychrometric chart number 1. And this is the ASHRAE. Oh, okay, this is just in English units. So this one is the same thing as the one before it, but this one here is metric units, and this one here is English units. So just use whatever chart is appropriate for the problem that you're working. So that's all for thermo. We'll look at heat transfer next. So for heat transfer, the things you really need to focus on are conduction, convection, and radiation. So here is really the beginning of the heat transfer section. So conduction is heat transfer that occurs through a solid. Convection is something that occurs through air, and radiation is something that occurs through a vacuum or just through somehow space, light, whatever. It sort of just gets there. So you'd have different formulas for each one, but those are the 3 main things you need to know. Conduction through a plane wall, heat will always flow from a higher temperature to a lower temperature. That is the direction, not necessarily up, but just from high temperature to low temperature. So you can have it through a planar wall, or you can have it through a cylindrical wall where we go like from inside to outside, etc. And then you can sort of work heat transfer problems similarly to an electric circuit type of problem if you account for the thermal resistance of the material that the conduction is happening through. And then you can just sort of draw it and approximate it as a resistor. And you can see the temperature drop, which would be like the voltage drop in an electric circuit. So that's what this is showing here. If you have a bunch of different materials, you just find the sort of resistance of each one, and then you can find the temperature between each one and get the heat, which is proportional to the change in temperature of that substance. A lumped capacitance model basically just treats the whole body as sort of like a particle, like the whole thing is one temperature, and doesn't really look at the difference in temperature from the outside to the inside. So if you are baking something in the oven, you know that when you pull it out to see if it's ready, you have to put a thermometer in and get the temperature that's at the center, because the edges are going to heat up first and the center is going to heat up last. But if you use a lumped capacitance model, that just approximates everything as sort of an average temperature. So it's an easier way to work a problem, even though it's not specifically accurate. But it just depends on how accurate do you need to be for your situation. And this is convection, but this is really pretty much it. So you may need to know a little bit about convection, but other than that, there's a lot more here in the heat transfer. But past fins, you probably don't need to know. So you might need to know the fins. Basically, what a fin does is allows stuff to cool off faster because there's more surface area where heat can escape. And they're used with convection. The faster the wind is blowing, the faster the heat is being removed from the fin. So that is pretty much where it stops. There's more stuff down here, but you don't really need to know all of that for the heat transfer section on the other disciplines exam. If you are taking the mechanical exam or the chemical engineering exam, you would need to know more than that. So here, this review, these are 2 review videos. These are actually for the AP Physics exam, but they did a really good sort of simplified overview of the theory and examples in thermodynamics. And then there are a few examples of heat transfer, like the MC delta T type stuff here in chemistry. But you would definitely want to look through your notes from when you took this class or from a practice book if you didn't take a thermo class, and use your cheat sheet and figure out what are the most important topics there. Just work as many examples as you can on the related sections of the exam that we see here. So you want to make sure you can work a couple of problems in every section. You never know how many you're going to have.